live stream on YouTube. So that's kind of our recording. So that one is on. And now we can do the present now using Google Meet. So you will see my screen share using Google Meet. Let me go find my OBS screen to share. There we go. Just found it. And there we go. Alright. Cool. And let me go back to Discord so I can keep an eye on today's text channel. Alright, so I got to today's text channel, and someone just posted, Aaron, posted a program. Okay, very good. So that's the base conversion program. Excellent. And we got a few more people coming in. And let me just check the time. We are about 2 minutes into the whole thing at this point. So I'm just trying to see if I can change the settings right now. Host control, quick access. Okay. Alright, so I'm not going to touch that because I think it's going to affect who can join us and who cannot join us. Alright, so let's go ahead and get started with today's class. The first thing to do is to work on the ungraded assignments. So there's nothing to turn in, but I want you guys to kind of think about base conversion a little bit. So what I'll do is I am going to show you a resource to do that. Alright, so we got more people joining us. Okay, admit. And one more. There we go. Alright, so a really kind of nice resource is onlinegdb.com. So it's basically kind of like a web client, for well, I shouldn't say web client. This is a website, where you can use GDB and also GCC or G++, to write your C or C++ programs. So let's go ahead and write a program to do at least one form of base conversion. In fact, we might even look into doing 2 different types of base conversion. And we got one more coming in. There we go. All right. So what I'll do is I'm just gonna change this program, this shell program to what I want to do. And no, I actually did not prepare a program ahead of time because I want to do it at the same time, so I can kind of explain the process that my mind goes through when I write programs like this. Okay. All right. So let's go ahead and get started with this. The first thing is, do we want to make this program so general that it can also deal with base 16, base 32, and even base 64? And you guys might be thinking, base 64, you gotta be kidding. Actually, base 64 is a standard used in web clients or web HTTP to transmit binary data using ASCII code, okay, using ASCII compatible code. So it's not really something that is fictional. It is actually real. But instead of doing that, I'm just gonna say const digits, okay, and this is going to be a char const char digits, and this is going to be an array. There are several ways to declare digits. We can make it a pointer, okay, and make it point to. Alright, so let's go admit more people. Okay. There we go. So I'm just gonna this will get me all the way up to base 36 because we got 10 digits from 0 to 9, and then we have A to Z as alphabets that we are borrowing from the English alphabet, as letters that we borrow from the alphabet. So these will form our digits, and then we have to write the code to actually do the conversion. Now I can make the user interface a little bit more fancy, but instead of working on the user interface, I would like to focus on the actual conversion of the base. Okay, so we'll go ahead and say we'll write a subroutine to convert from a particular base to the internal representation. Okay, so we'll name the subroutine of from base blah. Okay, from base, and then the first parameter that we want to pass is the base itself. So we can say that is just an unsigned, and we'll call it b. And then the second parameter is going to be the value, or the string that is expressing this. Well, okay, the string is actually the number that we're expressing. So we'll go ahead and use const char star, and this is our number. And we'll figure out what it's supposed to return. It's supposed to return an unsigned. Okay, unsigned. There we go. And here we have the shell of a subroutine. So the subroutine is going to take a base b. It will take a number represented as a string, and it is going to return the value, the internal representation of the value of that particular number. Okay, so that's what I wanted to do. Do you remember that I said I want this to be recursive? Okay, so in order to make this recursive, we have to think in a particular way. And the way to do that is to think about how to turn this problem into a similar problem, but except the size is like one smaller than the problem that we're given with. Okay, and the other way to think about this is to think about when can we stop the recursion? What are the simple cases we can say we are done? Okay, or the answer is going to be this for sure. Okay, so we're going to go ahead and figure out at which point can we stop and say I think we're done. Okay, so the first one, okay, my mouse is in the wrong window when I type this. So the first thing we can do is to say if whatever number is pointing to is null. Okay, so there are several ways to specify null. You can always use the Boolean operator and just basically put an exclamation point in front of star number. So basically that is the same thing as saying whenever number as a string, as a char pointer is pointing to a null character, we'll do the following. So in the following, what we're going to do is to say there's no value. Okay, we can just go ahead and return a 0 in this case. So if I use unsigned result to represent what we are returning, I can always give result an initialized value, which in this case means there's nothing for me to specify here. But I also have to remember one of my favorite mistake to use to make in when I'm writing programs is to forget to specify the return statement to return the value that we're supposed to return. Okay, that's my favorite mistake of all. So I kind of watch out for that. All right, so the next question is what if a number is not the null terminator in a string? In other words, what if it is pointing to something but is not the null terminator? Then what are we supposed to do? Well, it depends on whether it has a lot of digits or not. If it is just one single digit, then we kind of know what to do with it. If it has multiple digits, then we'll probably do it in a slightly different way. Okay. But we also have to remember that the null terminator is not a digit. It is simply a terminator. It is not a digit. So the test that we need to perform is a little bit trickier in this case because we know number is not pointing to a null, but we want to know whether the next character is a null. Because if that is the case, we also want to stop the recursion. Okay, because we are now looking at the least significant digit of a number, or the number itself only has one single digit. Either way, we can stop the recursion. So what we want to do is to say if number plus 1 is pointing to a null character, then we also do not want to perform recursion because it is just a single digit that we have to convert. Okay, so we'll put a comment here and say single digit, no need to call recursively. All right, forgot a semicolon on line 11. Oh, okay, there we go. There we go, thank you. Alright, so if we know that we don't need to do recursion and there's only one single digit and number is pointing to it, so all we need to do now is to look up the position of the character within the char string digits, the constant string digits here, and just want to find the position of that. So to do that, and I'm really poor when it comes to remembering things, memorization. So whenever I need to look up a function, to do something, I have to look it up. So I rely on the man page to do this. Okay, so now I can say man. Think I can remember the name. I just don't remember the parameters. So I think it's called string char. str string and then chr for looking a character. So let's see if that is what we want. Yep, locate character in string. Okay, that's what we want to do. So the first argument is the string in which C is representing the character that we want to look up. All right, so we go back here, and oh, I forgot one thing because I need to remember what to pound include. So we'll go ahead and pound include string.h in this case, and then we just supply our result here. So we'll say result is strchr, and then we have to supply the string first, which is digits in our case, and the character that we want to find is whatever number is pointing to. So number is a char pointer, and what it is pointing to is the digit that I want to convert. So what we are doing is we are looking up a character and convert it to the value that the character is supposed to be representing. Okay, so it is possible to do it without characters, without having to look up a string like this. The advantage of looking up a string like this is you can easily modify this program to deal with base64, because base64 uses punctuations as well. Let me just look up that base64 first, just so that you guys are convinced that I'm not giving you false information. So base64 is really a thing, and this is how they do the conversion. So let's see. So it goes from A to Z, uppercase, A to Z, lowercase, and then it goes for the digits, and then it has plus and a slash. Okay, so that makes up for
your face cam is over the
my face.
table.
Yeah, I know. I have a big face too. So I was told. Alright, so that should fix some of that problem right there. Alright, so we go from uppercase A to Z, and then lowercase A to Z, and then 0 to 9, and then plus and slash. So those are the characters that we can utilize in base64, which is a format that HTTP and other protocols can easily make use of in order to transmit binary data and have it embedded in a text string. So it is a real thing. Okay, so if I want to deal with base64 in the program that I'm writing, all I need to do is to change this particular string so that it is from uppercase A to Z, lowercase A to Z, 0 to 9, and then the plus and then the slash. Then this program will be able to handle base64 conversion, which is kind of cool. And that's kind of the flexibility of this program, the way it is currently structured. And I do know that sometimes we don't want to use a constant string like this just for that purpose, but this gives us the flexibility to only change one single string, and then we can now handle a different type of base conversion. Alright, so that handles the non-recursive cases, and now we can go to the recursive cases. So the else here is going to be recursive because we have more than one digits. Okay, so when we have more than one digits, then the first thing I'm going to do is to do it like this. Okay, result is from base, the same base that we're dealing with, and this time I'll use number plus 1. Now remember what number is. It's probably a very poor name for the parameter because it really is not a number itself. It really is a char pointer pointing to a character in a string, and the string itself is representing a number. Okay, but that's really long. Okay, so I just want to kind of point out that what number really is. So what this is going to do is it's going to ignore the character that number is pointing to right now, and instead it will just go like, let's skip this character, and then we'll try to interpret what the rest of the string is. What is the value of the rest of the string? So now the result is the value of the rest of the string, which is the less significant portion. Then we have to integrate the value of the current character, okay, what number is actually pointing to. So now we say result is result times, oops, take it back. Let's see. Yeah, we have a little bit of a problem here, don't we? Because we don't know the multiplier. So we first have to figure out the multiplier to multiply the digit that number is pointing to. All right, so that's fine. We can deal with that. So what we'll do is we are going to keep track of the power that we need to deal with. So we'll go ahead and use a local variable, unsigned. We'll just call it power, okay? And let's see. So we'll call this power, and power starts with the value of 1. Okay, and because we need to look up, how many characters is do we have, after the character that number is pointing to, so that the number of non-null characters after what number is pointing to is what we need to raise the power to. Okay, so we'll go ahead and do that calculation. So we use a for loop for this purpose. So we'll say for, and we'll need another local variable here. So we'll say another const char, we'll just say ptr in this case. Yeah, so we are doing a loop here, and because I'm using regular C and not C++, I cannot declare a variable inside the scope of a for. If you are using C++, or if you're using most scripting languages, you can actually declare a local variable inside the for block. Oh, okay. Yeah, that you can do that, but then you need to figure out the power that you need to associate with the character that you are dealing with right now, which is possible if you pass that along in the recursive call. So it can be done, but it's not super easy. So in this case, I'll just kind of get back to this one. PTR is going to be initialized to number plus 1, and the condition to stay in the loop is PTR is pointing to a non-null character, because the null character, the terminator, should not be counted as one of the places after the current place. And then for each iteration, the post operation is going to be power times the base itself. Okay, so we are basically calculating a power that we need to multiply the current digit the number is pointing to after we get result back. So after we get result back, we now say result plus equal to, and it becomes strchr digits and whatever the number pointer is pointing to, because that will give us the value of the digit that number is pointing to. But we also have to multiply this by the power of the base that we just calculated, and then add the previous result, which is calling from base recursively. So this result should be correct. Yeah. So there are different ways of looking at things. You can also, there's another way to do this, but I'll get this one done first, and then we might look at the other way of doing the same thing. All right. So I think the subroutine is done. Okay. So we can now test it. So to test this, we're going to have an unsigned variable, let's call that x here, and we'll say x equals 2 from base. And we'll go ahead and do something that is easy for us to check. So we're going to use base 10 because we know how base 10 works, right? So that makes it easy to debug. And we'll try something that's multi-digit but not too hard, okay? So 23 is good, okay, because it has multiple digits. It is a very easy value to convert, and digits are not repeating, so that should be a relatively easy case for us to observe and see whether the program works or not. Alright, so I'm still kind of keeping an eye on the text channel to see if people have any questions, and it doesn't look like we have a whole lot of question. And there's only one question of using the log of the number. Well, we don't really know the log of the number, do we? Because we're given a string, so we are not even given a value. And then the second thing is we want to avoid using math functions as much as possible. Log is not a very inexpensive operation. I mean, even this loop, by comparison, is not really too bad. I mean, depending on, of course, how long your numbers are. But log is a very time-consuming type of operation. Oh, we are not going to do printf. In fact, we'll get rid of the only printf here, okay? Because I do not like prints. I do not like printfs, okay? There's no need to use printfs to debug a program. If you are taught otherwise, it's time to change the way you debug programs. Alright, so we got everything ready to go, and then we will go head on to debug. Oh, no experience with recursion. That's okay. I mean, if you understand how subroutine calls work, recursion is a subroutine calling itself. So that's basically what it is. And let me fix this bug first. It's on line 26 right here, and it's complaining about assignment mix integer from pointer without a cast. Oh, right. Okay. And that has to do with what string char is returning. So getting back to the man page of string char, it says quite clearly that it returns a pointer to a character, not the offset. Okay, that's fine. We'll go ahead and fix that problem, because the whole idea is I want to convert into the position into the string. So I can just go ahead and say minus digits. So I have a pointer minus another pointer. Now this is going to have it's going to complain about this too. So I'm going to show you what it is going to complain about, and then we'll go fix it. Okay? Because I don't want to give you the right answer the first time, because that's not going to be helpful. All right. So let me just go ahead. Yeah, it needs to be casted, but we'll see. Okay? Let me see what you guys are talking about. Yes, we are going to use GDB. Yes, John Paul, that is what we're going to use. We're going to use GDB. And I am a proud user of GDB. Alright, so let's try to compile. And surprisingly, it let me do it. In other words, I can do pointer arithmetics. One is a const char pointer and the other one is a char pointer, and it doesn't mind doing that. Alright, well, I'm not complaining. So we'll put a breakpoint on the return 0 statement, and because I am overconfident of the program is going to work, okay? So we'll go ahead and run the program, and it is not terminating. And that's because it is an endless recursion. So what do you do when the program is an endless recursion? You do a Control-C, you stop the program, okay? And then you can find out where it is stuck. Okay, so we know it is in this loop here, and the problem is not that this is an infinite loop, it's because I forgot to advance the pointer, which is my other favorite mistake to make. Now, I know what my favorite mistakes are, so I can point to it right away. But if you are debugging a program and it seems to be stuck in an infinite loop, what are you going to do? So what you do is you look at all the variables, okay, all the local variables here, and then you perform another iteration. Okay, so you basically say step, okay, step, that's going to perform another iteration, and because it's on the same line, it's not going to get out, so we'll have to control C again to break the loop. But the thing is, if you look at PTR and you look at all of these local variables, none of them was changed. Okay, so if the precondition of the loop is true to begin with, and nothing is changed, for each iteration, the loop is not going to exit. Okay, so that tells us that, haha, Tech is probably forgetting to do something about that pointer, and I did. I completely forgot that I need to advance the pointer so that it points to the next character, because I was trying to count, how many characters do I have until I get to the end of the string. Okay, so if I don't advance the pointer, it's going to be pointing to the same thing over and over and over again. So that's not going to work. All right, so yeah, go ahead.
On the syntax on that,
Mm-hmm.
what is the comma indicating?
The comma here?
Yes.
Aha! Okay, I see that you guys have not been taught the magical comma expression. Comma is an operator in C and C++. Yes, I know it is surprising, isn't it? So if
So
you
does that mean?
so that means, okay, so let me explain what this is. This entire thing, oops, okay, too much. So this entire thing is one single expression. The outermost expression is a comma expression. So we have this sub-expression as the first part, and then we have this expression as the second part. And this is the separator of the two expressions. The value returned by a comma separated expression is really just the value of the last, or I should say, the rightmost expression. But in this case, the value of the expression is useless because we are only using the side effect of each expression. But a comma is extremely useful and confusing at the same time, because most people think that a comma is not an operator, but in C and C++, it can be an operator, it can be seen as an operator. Does that answer the question?
So it's allowing you to add the incrementation of PTR as another
Yes,
operation without making a new line.
that is correct.
Essentially what's happening?
Yep, yep. It's basically the way you can make a block of quote unquote statements, but in an expression. If that makes sense.
Do you know if that syntax is also correct in C++?
I believe so.
Interesting.
Yep. It's actually very handy sometimes, but it does make for very confusing looking code. Alright, so let's try this program again. So Tech is once again overconfident the program is going to work. So I just set up one final breakpoint at the return statement and just say, yeah, it's going to work. So we run. Okay. Alright. Okay, so I'm having a little bit of a problem here because it seems to be stuck. Oh, there we go. It's running finally. And it seems to be stuck too. Or is it just my... Nope. Okay, let me do this one more time. Run again. And we get to the return statement. So now, we can look at x, or the value of x, and I don't even need to print it. Sometimes I don't like this user interface because it is too easy. Because it already shows you all the local variables. I don't even have to say print x so that I can see what the value of x is. So it did do the conversion correctly. Okay, so it's working. Not really the best way to do it, but it is one way to do it. Okay, and you will find that sometimes I find the most obscure way of doing something because I think it is important to understand those different methods of getting the same thing done. Alright, so do we have any questions about this program? Can we walk through it now? Okay, yes, absolutely. So, how do we walk through a recursive subroutine? Okay, that's kind of a question. Um, and also, I want to address an earlier point that somebody made. Recursion should have been introduced in CISP 300 or 301, depending on which college you took the class from. And also in CISP 360, there should be some exposure to recursion. So I'm kind of surprised that some people were not exposed to the concept of recursion. But it's okay. Okay, in this class, we are going to do recursion in assembly language. Okay, so it's going to be fun at that point. All right, so what we'll do is we are going to track down this program and try to figure out how does it get the job done. Okay, and the best way to do it is to put a breakpoint at the beginning of the function that we want. That's kind of the focus of this discussion, which is from base. Okay, so if you say b from base, it will put a breakpoint at the beginning or the entry point of the subroutine from base. So this is really handy because I don't need to look up the line number and say, hey, put a breakpoint on this particular line. It figures it out, by itself. So I'm gonna go through the text channel here. Yeah, not too bad. Okay, scanning through a string is really kind of not too bad. All right, so we'll go ahead and run the program again. Okay, so run the program again. R is for running a program in GDB, or if you prefer, you can always just click on. I'm not sure whether run will do it or not because you need to kind of use the debugger to start. In this case, oh, there we go. So we got start, we got continue, we got step over, and so on. So if I do a R, it will run the program from the beginning. Okay, so it's not continuing. It is just going to run the program from the beginning again, and it will ask me, do I want to do that? And the answer is yes. Okay. All right. So now, what are we seeing? We are seeing that we are stopping at the entry point of from base, and so the next question is, okay, we are now in from base, but who called from base? Is this a recursive call from base itself, or is it the first call from main? This is also why I do not like the user interface, because it is too easy. It shows you what we call the this is called, no, not this one. This one over here is called a call stack, which is also called the backtrace. Okay, backtrace. So if you don't have a GUI interface, that is handy like this one, you can do it on the command line too. You can say BT, which is the abbreviation of backtrace, and then press the enter key, and that will give you an idea of how you got here. So from here, this is called frame 0, and this is called frame 1. So frame 0 is where we are, and then frame 1 is the caller of where we are, and then frame 2 is, if there's 1, is how we got to frame 1, and then frame 2. Frame 3 is how we got to frame 2, and so on. In other words, it would give you a hierarchy of function call of how we got to a particular point. It is extremely useful when you're trying to debug something that is recursive. Alright, so from the current perspective, we want to know for this particular invocation of from base, what is being passed, right? And we can see it in here that our local variable result is uninitialized, but it doesn't show the parameter. Okay, in other words, I do not see the parameter b and number, and for that, it's actually yeah. Go ahead.
Sorry, for that call for backtrace, does it show the most recent program ran, or does the program still have to be running? So like, do you have to add a breakpoint in order for that to work?
Your second interpretation is correct. The program has to be running, and you have to be at a breakpoint in order for backtrace to work.
Okay, thank you.
Yep. There are certain exceptions if you have what we call a core dump, which is the entire memory space dumped into a single file. You may be able to do a backtrace as well when you have a core dump, which is very useful because sometimes when a program crashes, it would just kind of leave behind a core dump, and then you can basically use a core dump for a post-mortem analysis. the core dump is the corpse of a dead program. That's actually a very accurate description too. A little morbid, but accurate. All right, so how did we get here? Well, we got here from main from line 44. So if you look up the program, line 44 is indeed a call to from base. So that's not really surprising. But from backtrace, you can also see that GDB does a pretty good job, telling us everything that we kind of need to know. Is what is B as a parameter? Well, it is 10. What about number? Number is a string. Okay, it gives you the address. But it also tells you, it also interprets the string as a null terminated string for us. So we know that string is 2, 3, and the null terminator is not displayed because in C and C++ it is understood that every string should be terminated by a null character. All right. So do we have any questions at this point? I'm just gonna switch back to Discord to take a look. All right, no questions so far. All right, so what are we going to do at this point? Okay, this is the execution point. So what we'll do is we will single step the program. If you like to use the user interface, you can always use step into versus step over. The difference is step into will go into a function call and continue. It will stop at the first statement inside the function that we are calling, and then step over, when you have a function call, it will just quote unquote step over, which means it's not going to stop at the beginning of the function that we are calling. It will stop after the function returns. Okay, so obviously in this case, when we're debugging something that is recursive, we probably want to use step into. So by default, I use step into unless I know I'm calling a subroutine that I know is going to be working fine. There's no need to get into that subroutine. So that's kind of the general rule. If you are using a straight command line because you're using SSH into a server or something like that, you can always use S for stepping or stepping into. So a lowercase s is the same as stepping into. To step over is called next, which is the same thing as pressing N and then a return key. So stepping, okay, so we are stepping into here. And from what we see over here, okay, because we know number is not a null string, it's not an empty string, so we know this condition is going to be false, okay, because number is pointing to a non-null character. So when we single step, not surprisingly, we get to line 23. So we're now checking what is the next character, is the character next to what number is pointing to, is that null? And we also know that is not null because we know that is the ASCII code of 3. So we know that we should skip to line 30 with the next single step. So now we're getting line 30, and it's going to get into this loop. So what this loop is doing is to say, not counting the 2 and not counting the null character at the very end, how many digits do we have? Okay, and we should only get 1 because it's just 3. So what we're doing is for each iteration, we are multiplying power as a local variable by b, which is 10. Uh-oh. No, why is it doing this? What did I do? Yeah, but why am I out? Did I click something accidentally? Because it just got out of the program. Fine.
The server might have timed out.
It could have timed out, but doesn't seem likely. But it's okay. We can just kind of keep going. Okay, so now we are done with that loop. And when we're done with that loop, power should have 10 in it. And that is correct because we just have to get past just one character. And to check whether everything is right or not, we can also check what PTR is pointing to, because PTR should be pointing to a null terminator in order to get out of the loop. So we can see right here, PTR is interpreted as an empty string. That's because PTR is pointing to a null. Now, if you're still not convinced, you can say print star PTR. So now we can see that it is definitely pointing to a null terminator. Okay? And now this is the fun part, because we are now calling from base recursively. So when we're calling from base recursively, the only change to the parameter is instead of passing number, I'm passing number plus 1. But you have to remember number is a pointer. So instead of passing the pointer to starting from the 2 in 2, 3 and then the null terminator, we're now saying, okay, let's move past the 2. So what we are passing really to recursively to from base is the pointer or the address of the 3 in the 2, 3 and then the null terminator. So let's go ahead and single step and see what happens. You can't edit source code. Oh, okay, that's because I put my mouse pointer at the wrong place when I click S. There we go. Single step. There we go. So this is really interesting because you can see from the call stack that we have main, being the root of all the calls, right? Because main is the first function being called, and it called from base, and then from base is calling itself. It also tells you what the line numbers are. So on line 44, main is calling from base, and then on line 33, from base is calling itself, and now we are at line 16, which is at the entry point of from base. So this is a really, really useful tool when you're writing anything, when you're trying to debug a recursive subroutine. And remember, BT can do the same thing, except it's better. It is better because it will also tell you what the values are for your parameters. B is just 10. Okay, that's kind of a given because we are passing the same base to all the invocations. But the most important part is when you look at number, this one is 3 and then a null terminator, and then previously it is a 2, 3 and then the null terminator. This is how we break a bigger problem into a smaller problem that has exactly the same nature as the original problem, and then we use recursion to solve the problem. Because we are breaking the bigger problem into a smaller chunk, but it has the same nature, and that's why we can use the same subroutine to solve that problem. So
is that the addresses before that?
Say that one more time?
It has 0x4006E.
Yes.
And that one is, so are those the addresses or are those
Yeah, that is an
values?
address. That is an address. That is the address of the 3.
Gotcha. Okay.
Yep. Okay. So when we single step through this, we'll get to line 17. We are not passing a null string, so it will go to the else of this. So we should end up on line 23. And when we get to line 23, then we are asking, is the character next, okay, right after the 3, is that a null character? And the answer is yes, that one is indeed a null character. So this condition is true. Line 23 has a condition that is true, so that means we will get to line 26. And then line 26 is looking up digits, which is a constant string that we have predefined on line 12, and is looking up the position of the 3, ASCII code 3, in that string. So when we look this up and go like, okay, the pointer is here. The address, would be corresponding to this character here. But when we subtract digits, as a string from the location of the 3, we get the net offset of the character in the string. So that means, after line 26, result should become just the numerical value of 3 instead of the character 3. So when we, I pressed the single step in the wrong window again. So when we single step, we can see that result now has a value of, I single stepped into the into the string char because I should have used n in this case. So let me see if I can use n. No, it's actually getting into the assembly code. So what I would do instead is to put a breakpoint here, basically to continue execution until we get to the return statement, so we can actually see what result is. But it's not letting me put a breakpoint here. All right, so let me see if I can do it here. Huh?
Step out of the function?
Yeah, we need to step out of the function, but we can put a breakpoint on line 37 and then continue. What? Sorry. No, it's.
Oh no. Okay, sorry.
Yeah, because we're in a assembly subroutine now at this point, so I just kind of skipped the whole thing because it wasn't letting me put a breakpoint on the return statement on line 37. So when I continue execution, it just went all the way back through.
Yeah, I thought that was what the step out thing next to the step into.
Oh, okay. The step out. Oh, okay. I didn't see that. All right. So this is just a quick. It was intended as a quick exercise of doing base conversion. You're kind of writing your own code to do it. Oh, the question from the other person was to use step out instead of once I accidentally stepped into something, I can use I can potentially use step out to get out of the function call that I'm in. So that was the comment. All right. So that is really just kind of a quick exercise. I haven't done the other one, from the internal representation, getting back to a different base. So I'm gonna save that for next time, okay? Because I think this is enough programming for a little bit, okay? But we also have to get back onto the course modules because we want to talk about binary addition today. So that's kind of this is where I'm going to leave off the base conversion for the time being. So now we are going to move on to binary addition. So I'm really hoping that everybody has a chance to read ahead of me. I saw one comment earlier, that says, still not fully getting what is look ahead, carry look ahead. That's okay. Okay, I just want you guys to have an exposure. I'm not expecting people to fully understand everything in the module because hey, if the modules are really that useful, you don't need me anymore, right? So let's go ahead and get started with binary addition. Oh, okay. So we can talk about the string char minus digits, maybe in the next class. Okay, so but for the time being, if you want to look it up, it is called pointer arithmetic. If you look up pointer arithmetic in any textbook or online, within the context of C and C++, that will give you the information that you need for that. Okay, so what I'll do is I'm going to turn on my tablet. Okay, so instead of reading my own notes, which is extremely boring, I'm gonna use the tablet to explain the concepts. And it is embarrassing that I have to say I don't know where I put my stylus. Oh, crap. Yeah, that happens sometimes. I misplace my stuff. Alright, well, if I don't have my stylus, I can still use a text editor for this purpose. But let me see if I can find it quickly. Alright, probably not. Oh, okay, that was a little disappointing. I was so hoping that I can use the tablet. But that's okay. We'll go ahead and use a different way to do it. There's always a different way to do something. Alright, so I'm just going to use a notepad for this purpose. So the idea is, how do you know the answer to these questions? Okay, so I'm going to give you an example. What is 6 plus 8? And these are all base 10. Okay, so we'll start with base 10 concepts, and then we'll move on to binary concepts. Okay, so 6 plus 8, we all know this is 14, right? Okay, that's kind of what we have learned over the years. But if you really just look at 6 plus 8 as 14, it's not going to help you with a multi-digit addition. So the other way to look at this is to say 6 plus 8 in base 10 is really a 4, but with a carry of 1. Is that okay? Is everybody okay with the concept of carrying in addition. All right, cool. And it's really not that big of a deal because all we are really doing is to look at the 14, the 1 in the 14, as the carry of 1. So to generalize this discussion, you can also look at 1 plus 4, in base 10 again, is 5 with a carry of 0. So instead of saying there's no carry, we now say there's a carry of 0. Is that concept okay? It's just really a change of terminology. Instead of there's no carry, we just say there's a carry of 0. All right. So now the next question is, why do we have the concept of carrying? The whole concept of carrying is because a single digit in base 10 can only represent a value from 0 to 9. So if the sum of adding 2 digits is exceeding the value of 9, then we cannot represent the actual result using a single digit. So we can only say that, okay, we have 6 plus 8 is a quantity that is represented by a 4, but also a 10. Okay, but the 10 is now seen as a carry to the next digit, to the digit that is on the left-hand side of wherever the 4 is. Okay, so I hope this concept is okay. All right, so now we move on to some notational stuff. Okay, so what we do is, I define a R function. So let me look up, whether I use uppercase or lowercase r, because I want to be consistent with my notes. And I'm using lowercase. Okay, so in base 10, okay, the result of adding 6 and 8 is a 4, but the carry of adding 6 and 8 is a 1. And likewise, in the second example, the result of adding 1 and 4 is a 5, but the carry of adding 1 and 4 in base 10 is a 0. In other words, I'm just adding some weird function notation here so that we can isolate what is the result as a single digit and what is the carry to the next digit, to the digit that is more significant than the one that we're adding. So do we have any questions about the R versus the C function? One is quote-unquote the result of the sum, and the other one is the carry of the sum. As long as the values or the parameters to C is from 0 to 9, then the answer is yes. The carry cannot exceed 1. Okay, so we got a few questions coming. I'm going to wait a little bit here for those questions. You can look at R as a mod. Yes, you can look at it as a remainder. In other words, if I generalize, okay, in base 10 at least. So in base 10, I can define the R function like this, right? So I can say, well, let's use unsigned because we are not dealing with digits that by itself can represent negative values. So we can look at unsigned R, having x and y. And remember, x is a single digit and y is also a single digit, and we're dealing with base 10. So in this case, it is simply returning x plus y and then the whole thing mod whatever base we're dealing with. But since we're assuming we're dealing with base 10, that is what it's returning. And then the carry function is actually also very simple. So unsigned c, unsigned x, unsigned y. And what carry is returning is even easier to look at, because all we are looking at is whether x plus y is greater than or equal to 10 or not. So is that okay? Does this help to kind of clarify what R and C are representing? Okay, excellent. So this is actually going to be useful later on too, because later on we're going to switch to base 2, and then we'll say, okay, what about base 2? Okay, so we got one more question coming, and then we'll go ahead and look at base 2. Okay. All right. So now the next question is, okay, well, it's not really a question, but I want you guys to kind of think about it. If you know someone who's young, okay, probably in second grade or so, learning, addition, subtraction, and stuff like that, um, um, adding two digits carry can only be 0 or 1. That is correct. Because the worst you can do in base 10 is 9 plus 9. So 9 plus 9 has a carry of 1. Okay. All right. So now the question is, what makes learning addition, subtraction, multiplication, and division so difficult? Well, it's because we, for whatever, actually for obvious reasons, we chose to use base 10 because we got 10 fingers. That turns out to be sometimes it's not a very good decision because the multiplication table in base 10 is kind of big, and then the addition table is kind of big too. I mean, just kind of think about if you are to explain to a young child, okay, why 7 plus 8 is 5 with a carry of 1. It's kind of difficult, right? Because you got it memorized, okay, and it's a pretty big table to remember. Even though addition is commutative, it is still a pretty big table. Just to get to, okay, what is 7 plus 8? What is 7 plus 9? What is 8 plus 8? 8 plus 9, and so on. I mean, it's not a very simple table to memorize. So if we switch around to base 2, what are we going to do? So this is one thing that I have never done before. This is the first time I try to explain base 2 addition in this particular way. So what I'll do is I'm going to take this, okay? I'll copy and paste this so we don't lose track of the original one, and I will make it general, okay? So I will say instead of using a particular constant as a base, I'll change it to b. In other words, you can kind of imagine that we have a const unsigned b equals to blah blah, okay? So it can be 10, can be 7, can be 6, can be 2, and so on. So now we look at all the literal constants of 10 and say, okay, that's just whatever the base is, and guess what? This is also just whatever the base is. Is that okay? Is this generalization of taking 10 as a constant, literal constant out, and replacing it with a constant, unsigned constant, is this generalization okay with you guys? Okay, I'll repeat that. We look at the function, R and C defined for base 10. Okay, we looked at this before, and everybody seemed to be okay with that concept. Okay, so in order to get to the result of R, we just add x and y and then mod it with 10, and we get the quote-unquote remainder, which is what I call the result of a single digit result of an addition. And then the carry is really looking at the sum x and y of x and y and see if it's exceeding or if it is at least 10. Okay? Yes, in order for this to make sense, x and y have to be single digits. That is correct. It has to be a single digit in whatever base we're dealing with. Alright, so now I just made a generalization. So instead of staring at 10 the whole time, I just go like, let's just make it a constant. So wherever 10 is, I replace it with b in this particular revision. Is that okay? But the logic still works, right? Because the whole idea of a carry is the sum of two single digits in a particular base is at least the base itself. Then we need to have a carry to the next digit, the more significant digit. That's the whole concept of a carry. And then R, which is the single digit result of an addition, has to stay within the range of 0 all the way up to b minus 1. And that's why the mod operation works really well, because that keeps us within that range. Is that okay? All right, so I'm not seeing any questions. Okay, so we're good so far. Okay, there's one more person typing. I'm gonna wait for that. Two more. Okay, and we got someone who's just coming to join us now. Cool. There we go. So now, so here's the magical moment. Okay, the magical moment is this. What did I just do? I just generalized a way to compute R and C to base 2. The mechanism is exactly the same as the one in base 10, except this one is going to work for base 2. In other words, in this particular case, okay, let me highlight which portion we are talking about. So in this particular case, x can only be a 0 or 1 because we're dealing with base 2 digits. So a single base 2 digit can only be a 0 or a 1, and so is y. Y can only be a 0 or 1. Okay? So now, if we are to figure out, the following things, let's try to figure this out. Okay? So we can say this is a truth table. Okay? X, y are independent variables. We want to look at the R of xy. We also want to look at the C of xy. Okay, so R and C are basically applications of the functions that are defined up here. And this time we just want to know what are the values. Okay, so x is a base 2 digit, which means it can be a 0 or 1. So it can be 0 or 1. And then while x is 0, y can also be a 0 or 1. While x is a 1, y can also be a 0 or 1. So we have 4 cases here to consider. So now the question is, what about R and C? Okay, well, you can plug it in. Okay, so if you plug in, 0 plus 0, and then which is 0, and then 0 mod 2 is still a 0. 0 plus 0 is a 0. 0 is greater than or equal to 2 is false, and hence a 0. And the next row, okay, this is going to be boring at some point. So we have 0 plus 1. 1 mod 2 is a 1. And then we have 0 plus 1 is a 1. 1 is greater than or equal to 2 is false, and hence a 0. No, we are not recreating NAND, but we're going to do something even better. Okay, it's going to be cool. Cool. Okay, so we got 1 plus 0 in this case. So 1 plus 0 is a 1. 1 mod 2 is a 1. 1 plus 0 is a 1. 1 is greater than or equal to 2 is false, and hence a 0. And then we have the funny one. Okay, 1 plus 1. 1 plus 1 is a 2. 2 mod 2 is a 0. 1 plus 1 is 2. 2 is greater than or equal to 2 is true, and hence a 1. Alright, so we'll go ahead and stare at the truth table first and see if there are any questions. Because this truth table is nothing more than just plugging in zeros and ones into x and y and try to figure out what is the result of R and what is the result of C for those cases. So let's see whether we have any questions. It is actually very Andy, not handy. No, nor Nandy. Alright, so what we'll do is we will now single out some columns. Okay, we'll single out, let's do the C column first. Okay, the C function column. So we single that out, and we just have x, y, and then the C of xy. Okay, so I'm just replicating this. There's no need to copy anything. This is just really kind of boring copy and paste right here. Alright, so if I didn't tell you that this column is corresponding to the carry of x and y, and I just say, hey, do you think you can find a Boolean operator that can give me exactly the same column? What would you say? Exactly. So yes. Nathan is right. It is and that's why I said this is actually very Andy. as opposed to handy or nandy. This is actually very andy because it is just and. Oh, okay. This is really cool. So this means for, okay, I cannot type. For base 2, c of xy is really the same thing as x and y. Woo, okay. The 1 plus 1 row for the carry or for the result? So I'm asking Rachel for carry. Okay, there we go. So for carry, all I did is to plug in, x being 1, y being 1, right? So now we have 1 plus 1. So this becomes 2. The base is 2, so 2 is greater than or equal to 2 is 2. That's mechanically why the carry of 1 plus 1 is a 1. But in terms of the semantic, if you can only have 0 or 1 as a single digit, and you are trying to represent the quantity of 1 plus 1, you don't have a choice. You cannot. Okay, there's no way to represent that quantity using a single digit. You need to rely on the more significant digit to say, hey, only you can help me out here because only you can represent a 2. That's why you have a carry of 1 to the more significant digit. Yep, okay, cool. Alright, so now we are done with the carry, but this is actually, I wouldn't use monumental to describe it, but this is actually a very important step that we just took something that was an arithmetic operation and we just turned it into a Boolean operation. Now, why is it important to turn it into a Boolean operation? Because we know that x and y can be implemented as x NAND y, the whole thing, NAND x NAND y. This is from the first day of this class. Okay, we looked at that, and then people look at this and go like, so what? Well, we know that NAND can be done using 4 transistors, 2 P transistors on top, and then 2 N transistors at the bottom. So we know that in order to compute the carry of adding 2 binary digits, we can use transistors to do it. That is the significance. All right. Cool. Well, I think it's cool. Okay, now we focus on the other one, the result, which is the single digit result of adding x and y. So I'm just repeating what we had earlier. So this would be 0 plus 0, the whole thing mod 2. 0 mod 2 is just 0. And then we have this, okay, which is a 1 because 0 plus 1 is a 1. 1 mod 2 is just 1. And then we have 1, 0. Same thing, because 1 plus 0 is a 1. 1 mod 2 is just 1. And then we have the funky one, which is 1 plus 1. We are looking at 1 plus 1, which is 2. 2 mod 2 is a 0.
It is on open mic right now, and it is very disturbing.
What? Sorry?
Someone is on open mic right now, and it is very disturbing.
Alrighty. So if you're not talking, can you turn off your mic, both on Discord and also in Google Meet? Alright, so I guess some people need to be reminded. So that would be Chris that I can see on Discord, Jonathan on Discord, myself, but I'm not going to mute myself. There we go, thank you. Oh, you're on push to talk, thank you. So we'll just have to be kind of mindful. Thank you. Alright, so now we got this table. Oh, okay, that's good to know, thank you. So maybe somebody already turned off the mic already at that point. Okay, Marco has a question, maybe? Or maybe not. Alright. So what we'll do now is to look at this table and go like, can we do something just like the other one? Converting this into Boolean operation. Well, the answer is yes. And Marco has it. Very good. It is exclusive OR. And then somebody's going to tell me and go like, we have never used exclusive OR. in C or C++, in CISP360, or in CISP300. So this is not something that I'm familiar with. Well, that's okay. That's perfectly legitimate. Okay. So what I'll do is I'm going to introduce you to the other way to express this. Okay. It's really the same thing as exclusive OR, but expressed in a slightly different way. Okay. So the way we derive that is to look at the two rows where we need a 1. So this row needs x to be false, y to be true, and then this row needs x to be true and y to be false. So the way we derive that, okay, is to say when we have a situation where x is false and y is true, then we want this column to have a true. Or when x is true and y is false, we also want we also want this column to be a 1. So if you are to evaluate this rather long expression, you would find that we have 0, 1, 1, 0. Okay? Which is the same thing as exclusive OR. Okay? So what I'll do is I'm going to use a shorthand now. Okay, this is where I transition to using a shorthand. So instead of using this expression, which takes a lot of typing because I need and stuff like that, I'm going to use a shorthand. So the shorthand goes like this: not x and y, or x and not y. Okay, that's the shorthand. We kind of talked about the shorthand on, I think, in the first class. Where conjunction or and looks like multiplication, we preserve the use of exclamation point for negation, and then instead of using or the two vertical bars, I borrow the addition symbol to mean Boolean or, okay, to mean Boolean disjunction in this case. This is a whole lot easier to type, and that's why I use this notation. Oh, okay, was someone in Google? Okay. All right. So I'm going to use this notation. This is actually doing the same thing as x exclusive OR with y, which turns out to be exactly what we want for the R function to do. All right. Is that okay? Cool, thank you. All right. So when there's only one thing I need to kind of make sure that people understand is when we perform the negation is applied to the one thing that is immediately to its right hand side. So for this particular negation, it is only applied to the x. Okay, so it is equivalent to this. Okay, because the exclamation point is only applicable to whatever is to its right hand side. So without using the extra parentheses, it would have meant exactly the same thing. But I just want to make sure people understand that negation only applies to whatever is to its right hand side. All right. But isn't this cool? Because we have just converted something that was arithmetic into now something that only relies on Boolean operators. Because when we look at the general way of computing R, okay, let me scroll up a little bit here. So when we look at the general method of computing R, it involves addition. This is arithmetic addition. This is not an OR, and also a modulus operation. But when we get down to here, for base 2, we can now say, hey, we can just use Boolean operators to do the entire thing. Yeah, this is way cool because now we know that for single digit addition, we can use just transistors. Now, if you use the method that I was introducing, just using NAND gates to do regular AND, regular OR, and regular NOT, yeah, this is going to take a lot of transistors. But the point is, it can be done. Okay. Okay. So the point is, now we know how to use transistors to calculate the single digit sum and also to calculate the carry of an addition. We have bridged arithmetic operations to Boolean operations, because then we can bridge Boolean operations to gate logic, and then gate logic boils down to transistors. So now we know how to implement this using transistors. But this is just for one single digit. So now we'll go ahead and talk about multi-digit addition. Okay, and if you think, oh, this is going to be hard, nah, it's not going to be hard. Okay, so we'll do it with base 10 first, and then we'll do it in base 2. So this is a base 10 example of a multi-digit addition. So let's try 700 and let me see here, 27, and I'm going to add to it say 356. Alright, so I want you to perform this particular addition, and most of you know how to do this, right? You know how to do this on a piece of paper, you know how to do it on in a calculator, and some of you probably can do this without writing down anything. You can just mentally do all the math. But what I want to do is to come up with a method that is systematic, because anything that is systematic can now be done using a program. It can also be translated into a structure using transistors or logic gates. Okay, so we want to use a very systematic way to do this. So let me first introduce the way I'm going to do this and give it some labels, and then we'll go back to actually perform the operation. So now we go back. I'm going to label this row X. I'm going to label this row Y. This row is called Q, but I'm going to also tell you what Q is. Okay, we'll define that in just a little bit. This row I call K for carry, and then this row I call S for sum. Okay, so now in this particular example, okay, X bracket 0, or if you want to use a subscript, that's fine too. But since I cannot type subscript easily using a regular text editor, it's really the same thing as X subscript 0. So that's just digit 0 of X, which is a 7. Digit 1 of X is a 2. Digit 2 of X is another 7. And then Y is the same thing. Okay, digit 0 of Y is a 6. Digit 1 of Y is a 5. And then digit 2 of Y is a 3. So this is just notation. Okay, I just want to expose you to the notation that I use when I'm using a plain text editor, when I cannot use subscripts. Okay, and sometimes I don't even use the square brackets. When it's clear, I just say x0 instead of x open bracket 0 and then close bracket. I just call it x0. All right. Now I want to know, how do I define the q bits, right? So q of I, okay, and I goes from 0 to 2. So q of I is defined to be the r of x of I and y of I. That is just how q is defined. Okay, that's that's also in the notes. Okay, if you look up your multiple digit addition, that's also how I define those specific terms. Except in the notes, at first I use the square bracket notation, and then at some point I would use the subscript notation. But getting back to the live example here, so the k bit is the carry. So this one is a little bit interesting. So we're gonna say we are not really sure what that is. Okay, we'll go back and get this one later. So, but those are the carries. And then when we get to the sum, okay, the sum of digit I, that becomes easy again. It is the r of qi and ki. All right. So let's go back to the concrete example and work that through first, because I think once we work that through, we'll kind of get a better understanding of what is going on. So now we go back to the concrete example, and we'll try to figure out what is Q0. So Q0 is the single digit sum of 7 and 6, and remember we're dealing with base 10 in this case. So that would be a 3, and we know there is a carry of 1 to the next digit. Okay, now how do we know that? Well, because we can apply the carry function, okay, for base 10. And then the digit 0 for the sum is the 3 plus the 0, which is just a 3. So now we work on digit 1, sorry. We're now working on digit 1, the column. 2 plus 5 is a 7, okay? And 7 plus 1 is an 8. Neither addition is resulting in a carry, so the carry of digit 2 would be a 0. And then 7 plus 3 is a 0 with a carry of 1, so I'm going to have to turn this to a 1 and then move the addition symbol over here. And then we have 0 plus 0 being a 0. And that's the end of the operation. And somebody's going to say, but what about this 1 over here? Don't we need 1,000? Well, when you're performing addition inside the computer, the width of xy and the width of the sum, they need to be exactly the same. So we have an overall carry of 1 in this case that is not represented as part of the answer. So I would say that one more time. The width of x, the width of y, and the width of the sum, they must be the same. So that means occasionally you end up with a carry of 1 that is just quote unquote hanging around and not be a part of the sum. Okay, so it just happens. It does happen like that. So are we okay with this notation? How I break up a multi-digit addition into these rows. We got x, y, q, k, and s. That is exactly, that's why CPUs have a carry flag, but we'll get to why the carry flag is really useful in maybe 2 or 3 classes. But for now, we just want to look at this and kind of get a general idea that this is how we perform multi-digit addition. Is that okay? So we got x, y, q, k, s, and we define the q bits as the r of xy. Now we want to know what is the k bit. Okay, the k bit is a carry. Okay, but when we look at k of I plus 1, there are 2 sources of that carry. In other words, when we add this digit and this digit, it can contribute to this carry. However, now I didn't have a single case in this particular example, but when we add this digit and this digit, that can also generate a carry to over here. So we have 2 sources of a carry. The first source is the carry of the xi and the yi, and then the second carry is coming from the qi and the ki. The big question here is, but Tech, you're being confusing here because you sometimes you use the plus to really mean addition, and other times you use the plus to mean or disjunction. Which one is it here? Well, I'm not gonna answer that question for the time being because it is because it would take some time to explain, and we are out of time for the lecture today. Yeah, time just flew today because I think I used the first part of it to explain how I wrote the code, and I spent some time to debug it, show you guys the features in GDB. So we are out of time today. We do have a lab today. So let me go back to the lab. And tonight's lab is for you guys to work on a multi-bit gate. So this is the lab here. And you cannot see it yet because I have not set it up. So I'm setting it up right now, which is also usually when I tell you what the passcode is. So in this case, the passcode is just multi. MULTI is the passcode or the access code of this lab. And I think you guys can get it done tonight. Okay, so we'll say it's due tonight. Today is the 28th. Like that. And we'll make it due at the end of the second lab for this class, which is 9:50 p.m. I mean, you're not gonna use all this time to do this lab. I mean, this is still a fairly easy lab, but I do want to explain a little bit before we move forward with this lab. So we'll do a save and publish. There we go. There we go. Okay. So let me explain what is a multi-bit gate. Okay. We haven't had a chance to talk about this just yet. So we know what is a single bit. Yes, the passcode is indeed multi. Very good. Okay. So I'll just use AND, for this example. So we'll say, what is for a regular gate. Okay, if you use a regular gate, it is a single bit gate, which means the input pin can only handle 1 bit. Each input port can only handle 1 bit. But when you're dealing with a multi-bit gate, then you're looking at something like this. Okay, so we'll say x3, x2, x1, x0. So the x is representing one port of an AND gate. So that port actually has 4 bits, in it. And then the other port of the AND gate, we'll call it Y, also has 4 bits. So it's Y3, Y2, Y1, Y0. And if the gate is an AND gate, okay, so we'll specify an AND here. If the gate is an AND gate, then the output port, which is, there's only one single point of connection, but that one single point of connection has 4 components in it. The first component, well, the most significant component is actually x3 logical AND Y3. And then the next component is x2 logical AND Y2. And then we have x1 logical AND Y1. And then the last component is x0 logical AND Y0. So yes, I know things are not exactly aligned. Let me fix the alignment. Like so, and everything looks good now. So that is what we call a multi-bit gate. So in LogicSim, this is one port of the input to this particular AND gate. This is only one port to this particular AND gate, and this is what the output port is going to specify based on the input. So when you look at this as a single AND gate, a multi-bit AND gate, it still only has 2 input ports and 1 output port, just like a single bit AND gate. It is only when you look at the properties of the AND gate that you will see that the bit width is 4 instead of 1. That is how you specify whether a gate is a single bit gate, which is the default, or you want to turn it into a multi-bit gate, then each port can take on multiple bits. So that's kind of what your lab is going to be doing. Let me just kind of quickly go through a preview. I mean, you guys can see the lab already. It's already released, so if you want to jump ahead and go do it, that's fine. So the first question, all of these questions are really just steps of, configuring an AND gate, to perform the operations, and also just to get used to the properties of a gate. Okay. And also to look at the error messages, when there are error messages. So for the most part, oh, by the way, when you look at the output here, this is the one part where most people have questions to ask. You just type in the exact value that is displayed in LogicSim. That's all. Now, if Canvas decides that, hey, all of these leading zeros, we don't need it, and get rid of all the leading zeros, that's okay. It's not a problem. Okay, so it's okay not to have the leading zeros shown in your answer. Now, if the answer is actually a 0, Canvas will also tell you that this particular question does not have an answer. That's okay. When you submit, it will actually take your it will take your answer of a 0. It's not going to say it is missing an answer. Yeah, this part has a splitter, so you kind of have to remember how to use a splitter from an earlier lab. And then we got question number 6. Question number 6 is is a funky one. Okay, so question number 6 has to do with how we compute the bits. So we got the K, we got the Q, the P and the G. Oh, darn it. Okay, fine. I will give you a pointer to answer this question. So it is asking about something that I haven't really talked about yet, but it's a very simple thing for the most part. So the P and the G are defined all the way down here. So let me tell you where they're defined. It's a very hidden way to define those particular terms, but it is defined here. It is defined right here. So this is how P and G are defined, and I will do you guys a favor. Okay, so I'm gonna do a screenshot and put it into today's text channel, unless somebody beat me to it. And I know you guys are fast. Because this is the only part that can be a little bit challenging, is where do I find where P and G are defined? It is now in the text channel. Alright? So you have to look at how these terms are defined, how Q is defined, how K is defined, how G is defined, and how P is defined. And I cannot remember what the other one is. Oh, where's my question? There we go. This is the lab. There we go. So we got K, we got Q, we got P, we got G, and we got S. That's it. Okay? And you will find that some of these have a particular pattern, and that lend itself to being able to be implemented using a multi-bit gate. One of these is different from the rest, and it has to do with the indexes. Okay, what the index on the left-hand side of the equality and the indexes on the right-hand side of the equality. 4 of these would share a common trait, and then the 5th one is different. So that is going to be what you need to find the answer of question number 6. And I believe this is the last question. All right. Okay, so please do not share your answer or what you think is the answer in the text channel, because everybody should be working on this independently. And the answer is, I'll give you guys a clue. It is not G. So now you can rule out that one. All right. Alright, so I'm going to leave it up to you guys to work on the lab. I'll grab a quick bite, but then I'll come back to the text channel and see if there are any questions. Alrighty. So I'm going to turn off my screen share and my voice chat from the 3 sources. First there's Discord, and then we have Google Meet,